The topic now is regression. Regression is, as we talked about, making a guess of the relationship between input and output. Does that make sense? Suppose I have the data. We took the example yesterday of a young entrepreneur trying to sell ice cream on the beach, ice cream shack, right? So what does the entrepreneur has to do? And why is the some data needs to bring some data which says ice cream sold, how much of ice cream you will sell in quantity, right? So input is a number, output is a number, isn't it? But see, what happens is, and this is where in machine learning we talk of two things. We talk of something called the ground truth. There are some very complicated weather dynamics that relate, that affect the temperature in a place. The temperature itself affects how much ice cream the boy will be able to sell on the beach. The young entrepreneur will be able to sell on the beach, isn't it? And as we talked about, temperature is not the only factor. We can have other factors like wind speed. It's a very windy day. Parents might not bring their children there, or there'll be high surfs. You know, you all get surf warnings. Like, don't go surfing today. It's very windy, right? And precipitation, if it is raining, you wouldn't go to the beach. So all of those factors are there. But to get started with regression, we are going to oversimplify and say that let's take temperature, one dimension. Extending it is very logical, right? So in one dimension, the intuition is easy because pages or like this writing board is two-dimensional, isn't it? The screen is two-dimensional. If I use one dimension for the output, I'm left with only one dimension for input. So the ground truth is, what is the real relationship between X and Y, right? And so we use the word ground truth. This word you'll find very common in machine learning. The ground truth is, now there are two aspects to the ground truth. One is the actual Y for a given X. So you say that given Xi, a particular data point, let's say 1, 2, 300. So some particular ith data point will be some value of Xi. You happen to know some value of Yi, you know it, right? So ground truth is this. This is the empirically observable truth. You measured it, isn't it? You have a table of it. Underneath this, there is also a ground truth function, the real relationship, which caused Yi to be equal to Xi. Does that make sense? Except that we don't know that relationship. When you get a table of data, it doesn't come with a ground truth function attached. You don't know it. What is our job? Our job in regression is, and so now another interesting thing, remember that the output Y belongs to, it's a real number. Now, when you see this R with an unnecessary vertical bar, it's the mathematical symbol for number, a real number, as in it could be a fraction or anything. 3.14 is a real number. Sometimes, so this is very, very common, and this is how we will start. But just for the sake of parking that fact, it need not be a number. It could even be a vector. The output could be a vector. So for example, if you're predicting the wind tomorrow at noon, wind has two qualities to it. People won't just say it will be 5 miles an hour. They will want to know 5 miles an hour in which direction, right? So for example, wind coming inland, from inland, will be warmer. Wind coming from the ocean will be colder, right? During summers. In summer, you would love to have wind coming from the ocean, from the Pacific Ocean. So in that case, Y could be, it will be n-dimensional vector, right? Now, a little bit of convention in our field, we represent vectors. See, when you're in school, how do you write vectors? You say vector with a big arrow on top of it is some component I plus Yj. Let's stick to 2 dimensions. Are we all familiar with this notation? Right. So we need to retrain ourselves to a different notation, because this notation is not used in our field of machine learning for a reason. we'll run out of letters in the alphabet because data is often in 100-dimensional, 200-dimensional, 1000-dimensional spaces, right? For a lot of natural language processing, these days, we are talking of dimensionality in the order of 300,000 dimensions, right? So huge dimension. So we don't do that. What we do is we write a vector as equal to, the first thing you would do is x and y. This is your vector, right? And people may not choose to even put the arrow so long as they write it. If it is implicit that, so it need not be, people will just say, if it is understood that it's a vector, people don't put an arrow on top of it. Are we together? In fact, most of the time you won't find arrow. Sometimes what people do is they make it bold to symbolize that it's a vector in this field. The other thing that you do is, and this is a machine learning convention, you reserve y always for output. So then writing vector like this wouldn't be meaningful. If you have a vector, let's say that input is temperature and wind, let's say it is rain, precipitation. Let's just call it rain. How much it is raining. So at any given time, data would be some amount of temperature and some precipitation value, rain value, right? How much raining it is. It is a point in this space. When you are looking at input data, it is conventional to mark the axis as x1 and x2. You don't mark them as xy. Are we together? Right? You call them x1, x2. The advantage is when you are dealing with, let's say, 30-dimensional data, you can still say x1 all the way to x30. You don't say that, oh my God, English, I ran out of alphabets. IJKs. You can do that. So you would say that the x vector is x1, x2. You would write it like this. Okay? So this is just setting the convention. Now, one more thing, observe the hat that I made this thing wear, y hat. Whenever you make a prediction, predictions, it's a convention in our field to make the predictions wear a hat. Right? It's a convention that you should follow because it makes it obvious to the community. Right? So y and y hat. Now, the ground truth is G. Whenever I write G, it means it's the ground truth. It's usually unknown. Right? You don't need it. But the purpose of machine learning is not to find G, but to find a proxy for G. Something, a function, this. Your job is to find something that is an effective replacement for G. It's a hypothesis. It's a model. You make a model in your mind. You make a model. You say, tell the machine, come up with a model, which is another word of saying, create a guess, make a hypothesis of what it is that best matches the data. Because it doesn't matter. Ultimately, you have to do practical jobs, make predictions. Given any set of data or any range of things, you can create infinitely many very effective models, right? So the only question that remains is, did I make a good model or did I make a bad model? So we need some measure to tell whether the model is good or not, isn't that? So how would we do that? Let's go through the intuition for that. Suppose you have points like this, and this set of points, and I ask you that I'll give you two hypotheses. Let's first deal with straight line hypothesis. I make guess number one, that the relationship between the x1 and x2, should I make the axis also, guys, or is this understood? x1, let me just say xy, suppose x and y. So I'll make two hypotheses. One hypothesis is this is the relationship. Another hypothesis would be that this is the hypothesis. So let me call it hypothesis A, hypothesis B, right? And let's take another hypothesis, C. Which of the hypothesis or model you think is probably the more more effective in predicting values. If I give you X, it will better be able to predict Y.
See.
The green one, right? Intuitively you see that it is this. But how would you quantify it? How would you make it obvious to do that? Suppose you have points like this. So just to recap, we said, suppose you have points like this. Let me throw in some point. And you make multiple hypotheses. So suppose you made a hypothesis like this. You made another hypothesis like, let's say, A, and you made another hypothesis, let's say, this, B. Right? And your data, the axis is, this is your Y and this is your X. You're trying to discover a model, a relationship between X and Y. You would all agree that C is better, isn't it? There's something to be said about B. B is what is called a null hypothesis. Hypothesis. The pen has started working. The null hypothesis. Now, what is a null hypothesis? It is the claim that Y does not depend upon X at all. So changing the value of X does nothing to Y. So the best thing to do is just to take the average of Y values and claim that's the prediction. Right? So you say ice cream that you sell has nothing to do with the temperature. You will sell the same amount of ice cream. Obviously, the null hypothesis is wrong here in view of the data. A is even worse. You're making a hypothesis that the more the temperature rises, the less ice cream you'll sell, right? And it doesn't. So now, what is the thing? What is the intuition that makes C right? Why did you pick C? The intuition that you picked was C is closest to the data, isn't it? C is closest to the data. What does closeness mean now? I'll quantify it, and that is the great work, by the way, that Carl Friedrich Gauss made in 1793, and later on was published in Legendre's paper, Method of Least Squares. So let's rediscover history. Suppose this is a line and you make some points. What you can do is, you can see that, so now let's look at this. This is some value xi, isn't it? This is reality. This is y. This is the actual reality, yi, isn't it, guys? But your line actually, your line, what is this point? This point is your y hat, I. For that value of x, for that temperature, your line is telling you that it is underestimating how much ice cream you would sell as an entrepreneur, isn't it, guys? Right? Y-axis being ice cream and x-axis being y, x. This is ice cream. This is temperature. So this is it. So how wrong were you? For every point here, you can therefore create an epsilon. This is the measure, epsilon I. The difference between prediction and reality is a measure of how much error you made. Isn't it intuitive, guys? Isn't it obvious? And now the thing is, someplace you would make negative error, for example, epsilon j, right? Because here, yj is here, xj is here. Sometimes you make positive error. But see, at the end of it, what matters is not whether you overshot, overestimated, or underestimated. What matters is the magnitude of it. Like, for example, the blue line is making only underestimations. So it doesn't mean that it is making very less errors. It's making huge errors. Do you see that? Huge difference between the blue one and the reality, right? So from that, we derive an intuition that error, if we just look at the magnitude of the error, not its sign, that is a good way, and add up all of the mistakes, right? This could be it. It's a positive quantity, magnitude. So now you can say that the total error would be something like this, right? Now comes an interesting fact. You could have done this. Now realize that so long as I take this, I could raise it to any power. I could have done this, the errors square. What happens if I square the error? It's still positive, right? In fact, I don't even need to put bars there, right? You could cube it and so on and so forth. So now the question is, what should I use as my notion of mistakes? This is called the sum squared error. Right? And if you average it over, sum squared error is this guy, right? And this is called some absolute error. Does that make sense? Because you're taking the absolute values. And if I average it, average over n points, so suppose I have n points, suppose I do this, epsilon I, where epsilon, at any epsilon I is a yi minus yi hat, the difference between prediction and reality, right? Then suppose I do this and square. What is this? This is average, mean squared error, MSE. And most AI libraries, they usually take this as a default measure. Mean squared error is this. Does this make sense? Common sense to intuition? And mean absolute error would be very similar, epsilon I. Now you say, no, wait a minute. Given this epsilon, I could have done all sorts of things. I could have taken the cube power, the fourth power. I could have done sine, I don't know, some weird function of that error. So then comes a theorem that I believe dates back to 1806 or 1812. Let's just say way, way back. It is colloquially called the blue theorem. Like those of you who have done a lot of, how many of you have done a lot of statistical analysis in your management courses, quantitative management? Right? So it's called the blue theorem. Right? What is the blue theorem? You should tell me. Okay, blue is a BLUE. It stands for best linear unbiased estimator. Now, this is in statistics, it has a whole set of meanings. So I'll explain what these meanings are. Best is, of course, easy. Linear is when you're trying a straight line model hypothesis. Estimator is literally a hypothesis. But what is this biased versus unbiased business? It turns out it had nothing to do with politics. What is it? You go ahead.
It's like a random sampling. You are not taking that data just from one day, for instance.
Yeah. Yes, you're right, but I'll just make it more formal. See, guys, here's the thing. Suppose I tell you, find the average height of people, or just say, what is the average volume or weight of apples? Now you have two choices. You can go and collect all the apples in the world and then take the average, because that is the full population of apples would be all the apple trees in the world. Or if I ask you, what's the average height of humans? Well, you'll have to line up 8 billion human beings and take their height. Not practical. So what would you do? You would just go and take a random sample of human beings. Just don't be silly. Like, don't go to a kindergarten and only take kindergartners. They'll be not so tall. Or don't go to a basketball court and pick people there. But you take a representative sample. So you sample from the population. Right? Are we together? When you sample from the population and use that to compute something, your hope is that that something that you computed, that statistic that you computed, mirrors the other reality about the population, isn't it? So in other words, if you take just a population and you found the mean of the population, you would hope that it is close to the mean of the whole population, right? Up to minor errors. Does that make sense? Or if you take many samples, then it would certainly be average of averages would be pretty close to the population mean. By the way, that's a center limit. We are coming to that in a moment. Now, here is the interesting thing. For certain statistic, it is true. Like, for example, for mean, it is true But weirdly enough, it is not true for variance, standard deviation. It turns out that if you had the full population and you did the standard deviation of that truly, and if you did the standard deviation of a smaller population, any simple sample that you take, your sample will always underestimate the population's standard deviation, right? So, for example, how do you find the standard deviation? I'll use this area. So, suppose,
Asif, one quick question. Sorry, before
yes,
actually related to this blow, like the unbiased estimation, we see normally a lot of polls, surveys, and others also, right? Which is collected across population or in a particular city across demographics and all. At that time,
yes.
also, do you think?
No, Vagish, you're right. It is
mm,
true. See, that is not a mathematical, the mathematical definition of unbiased is what we are explaining. That is a social bias. See, what happens is that is the representativeness of the sample,
mm,
how well the sample represents the overall population. The
mm,
problem with this so-called polls is that it is almost impossible to make a sample represent the population for a simple reason. Most polling, I mean, first is incompetence. Most of the polling centers are lazy people and they
mm,
keep asking the same set of people for their opinions.
true.
The other is actually a deeper problem. The people who are unwilling or who don't like to express their opinion, right, will not tell you. They won't participate in the poll. It is not a mandatory participation, isn't it?
Yes.
So even if you pick a random sample of human beings, there would be a silent subset that simply wouldn't vote or give you their opinion either way. So what happens is opinion is often controlled by the population that you can reach and and within that the population that is opinionated, and which is why it's a little bit harder to do social polls, get it right. People have created all sorts of models by doing meta polls and so on and so forth. So um, that's a different thing. When we speak of unbiased here, what we are talking about is if genuinely you took a representative sample, you put in your very best effort, and I assure you that your sample is quite representative. Then that statistic that you create out of it, can you believe that it will be the statistic of the uh, full population? So I'll give you an argument why variance doesn't work, standard deviation. So suppose your data goes from here to here, all the way. Are we together? This is the range of the data. Any sample you take invariably will have a min and a max, isn't it? How likely is it that when you take a random sample, you have included the extreme min and max of the population? Very unlikely. If you take a sample of children, what is the likelihood that you happen to have the smallest child and the biggest child in the world in that set? Not likely. So you'll end up with something like this. Your population, sample population distribution will be like this green line, green curve. Does that make sense? Right? And so the variance of this, the spread of this is less than the spread of the entire population, which is one reason. So think about it. How do you give the variance? Variance is the square of standard deviation. Variance, sigma squared, is usually you would call it the values xi minus mean squared. Remember, this is it. X bar mean, I'm writing mu, the mean, isn't it? And this divided by, and in school you're told that if you get a bunch of numbers, you do that. But if you know, actually, let me put capital N here. When you do it for population, you put a capital N, right? But you know that when you just have a sample, you are underestimating the variance. So what you can do and what people do is they replace N with N minus 1. That is why in machine learning literature, where you always deal with sample in AI, you always have a sample of the data. You don't believe that that is all that there is in the world, right? So you will often notice that sigma square, which is variance, a square of the standard deviation, is always written with a minus here, xi minus mu, xi minus mu squared. Are we together, guys? Right? This and that explains the mystery of why you keep seeing. Now, why minus 1? it gets a little bit more complicated, but you realize that if I make the denominator a little bit smaller, it will make the overall quantity a little bit bigger, right? So the hope is that it will stretch this into this, right? You'll have a better estimate of the true. So from that we gather that mean is a unbiased estimate. Variance is a biased estimate. You have to make it unbiased with a correction. That is the meaning of that. So, well, there is a theorem called Gauss-Markov theorem, which is generally called the blue theorem, colloquially, especially in management classes, which basically says that if you have to choose epsilon, the absolute value, or you have to take the square of this error, cube of this error, of all of them, the best choice is square. It's a mathematical result. A collinear situation, and there are certain conditions in which it is true. It's not always true. There has to be certain homoskedasticity in the data. Now that's a big word, right? And heteroskedasticity and so on and so forth. If you have heteroskedasticity, then you have to run away. Then the theorem wouldn't work. You have to do a power transform in the data to make it more reasonable. That's one of the things I've added to your labs. You can read about it, but I won't go into it. To find the real linear relationship between input and output. So if you remember the story of Mary Poppins, anybody remembers? I've shown your children the story of Mary Poppins. Nobody knows Mary Poppins. Okay, there's a lady who tries to increase the confidence of children, and she says, use a really big word. Right? And there's a word I'll remember. I used to love that word. Okay, some very big word, and people will be impressed with you. So, well, in this topic in regression, right? If you can always ask, oh, and does your data have heteroskedasticity? What is that? But anyway, I'll explain that later. Let's move forward from that. So you just square. That is why mean squared error is the most common measure. So now what does it do? It helps me distinguish, I don't know why the colors changed, but it helps you distinguish between the best model and the not so good model, isn't it? Now the question comes, how do we discover, how does a machine discover the best model? Right? So there are two ways of doing it. Let me see if I can do that. Oh, I don't know what is going on here. Okay, there are two ways of doing it. Let's say that you get data like this. I'll again do that. And I'll make it sort of intuitive. So, and suppose you have to find the best fit line. So you can start. So in engineering, engineers are confident people. If you ask them a question, do you know how to do this? They'll say, of course. And later on, they'll figure out how, right? Or they'll just guess. Okay? So in the same spirit, let us go guess. We viewed this hypothesis. This is our first guess. Now, how do we find the best one? What you can do is you can go on drawing lines and then one of them will be fit to the data. Is that a good approach? Why not?
Trial and error.
It's trial and error. It has one problem. First, you'll burn a lot of compute. Secondly, there's no guarantee that you have discovered the best line, isn't it? So that reminds me of a sorting algorithm. All of you are familiar with bubble sort, quick sort. Quick sort is supposed to be better. Merge sort is better than bubble sort. Why? Well, bubble sort is n squared, horror of horrors, right? Whereas quick sort, merge sort, etc., n log n, much better. But there is a sorting algorithm that beats them all in being inefficient. So it will make the bubble sort look good. So it is the BOGO sort. What does it mean? You have a bunch of numbers. What you do is you just shuffle them. Now stare at it. Is it sorted? If it is not, say, oh shucks, let's do it again. Shuffle it again and keep doing it till it gets sorted. Now you can prove that this is a valid algorithm because it does have an end point. It will end eventually, right? But that's not the one you want to try, right? Or that's not the one that you want to implement in your system. So in the same way, drawing lines like this is like doing bogus sort. You don't want to do that. What you want to do is you want to have each of the lines somehow find the shortest path to smoothly glide and fit to the data, get attracted to the data. So here is the intuition I'll give you guys. Imagine that each of the data points is a piece of, let's say it's a piece of positive charge, and your line is negatively charged. So what are all of these pieces, all the data points doing? They're attracting it. And what will they do? Whichever way you put the negatively charged line, it will gradually, smoothly move and fit into will go through the negative pointed data. I mean, the data, positively charged data, isn't it? That is the process you want. Now, the intuition for that is called, and I'll put the word there because this is another celebrated thing in our field. So what is the intuition here? I will tell you, first I'll show you the intuition. See, we realize that we put the function, suppose we have an equation of a line, y is equal to, we hypothesize the line. So typically in school, you write it as mx plus b or something like this. In machine learning community, we don't use this notation. What we do is we call it theta naught plus theta 1 x. This is, and here's one way to, and some people write it as beta naught plus beta 1 x. Right? Doesn't matter, theta, beta, whatever you use. One is the intercept, the other is the slope. Now comes an interesting point, which is that in any given situation, it is happening here, but okay. So this is the real world of data. And this is a world which I call the hypothesis or model world, hypothesis or parameter world. These beta naughts, these are called the parameters of the model. Right? These days you hear that LLMs have 70 billion parameters, etc. That's what they're referring to. So in the parameter space, whose coordinates are, let's say, beta 1, beta 2. Now observe that in real world, any line that you draw in the real world, let's say I drew the line A. This line has a slope and an intercept, isn't it? And therefore, in the hypothetical world, it will represent a point. In the parameter space, it will represent a point. You see the duality here. In real world, hypothesis is a line, model is a line. In the parameter world, it's a point because it's a space of hypothesis. Every point is a hypothesis, is a good model. Right? You drew another point, you have, well, another B would be maybe here, some other point, so on and so forth. Right? Are we together? Yeah. Now the thing is, we also realize that the error, the total error that we wrote, which I'll just write it as L, was y minus y hat I, let's say squared, summation of this. And I'll forget about 1 over n, just write it as, or maybe I can put it 1 over n. But let's remove the clutter. You can assume it's averaged out and so forth. This is equal to yi minus, what is y hat? Beta naught minus beta 1 xi, the actual expression. So far, so good, guys. Right? Now notice, if data is given to you, you have to find the best model. Finding the best model means finding a line whose beta naught and beta 1 are so good that the loss takes the minimum value, isn't it? Isn't it, guys? Yeah. You have the least error. What is that beta naught beta 1? Because if you know that beta naught beta 1, you have found the best point in the parameter space, therefore the best line in the real world that goes to the data. Now, stare at this equation, and then there's a I over, the summation over there. Stare at this equation. When you stare at this equation, can you change the data when you're training the model? No, that's cheating. Data is given. You're trying to fit to the data. Right? So in this, what knobs can you really turn to make a better model? Just the parameters. You can change the parameters, isn't it? So basically, loss is a function of the parameter vector. Parameters, right? Beta is this vector, beta naught, beta 1. So any one point, for example, beta A is this point. Does that make sense, guys? And we are trying to find. Now look at this equation. This equation is what? Is it, this is a quadratic equation, isn't it? So losses will be positive. Now, what do quadratic equations like this look like? They have the shape of a parabola, isn't it? Will it have a shape like this? Make sense, right? So because it cannot be negative, it has values for every value. You can convince yourself. One easy way is, what's the equation? What is this equation? Y is x squared, right? So in the same way, it is a parabolic in these parameters. So now that you got that intuition, we come to the final part of our discovery, and in fact, the foundational idea of machine learning. All algorithms, whether they're whichever fancy algorithm we have today, ultimately, this is the way they learn. All right, guys, bear with me. I will try to open another thing. I'll reopen this application. That seems to be the only way on this machine that I'm able to get a new. And next time around, I will have something better. Let's say one note. Okay, here we go. All right, we have an empty page, fine. So just imagine a function. Let's say that I have a function like this, right? And my goal is, what are you trying to do? You're trying to find the point at which the loss is minimum, right? Let me just take one of the parameters, some beta parameter. Let's say beta 1, it doesn't matter, right? Now, let us say that you made a random guess. You picked a random line. That random line will have some beta naught beta 1. Suppose that point was here, at this point. Let me just call it A. Let me call this point B, right? At this point, now tell me, guys, what is the slope at A? So let me define slope. Slope is defined as, it's quite literally very intuitive. If you take one step forward, forward means in the positive direction of X, do you gain height or do you lose height? Right? Besides that, most of you go hiking. You say it's very slopey, right? The slope is very strong here, or the gradient is very strong gradient. What do we mean when we say it is a strong gradient? Oh, you're huffing and puffing because you walk a little bit and you have gained so much altitude. That literally is the definition of gradient, and in one dimension, the slope. Right? How much does it change if you move forward in one unit? So in this, if I move forward 1 unit, am I gaining y value or losing it? Losing it. So the slope here is negative slope. Now, so suppose I'm here and I say, let me find a better point, a better value of beta 1. From A, would it be okay to say that if the value is A, then what I should do is, if I know the slope dl, d beta, if I know that the slope is negative, but I want to move forward, tiny little bit, I want to move forward. How do I do that? I need to take the negative of that to make it positive. And then let's not take a big step. Let's take a very tiny step, alpha. Tiny little bit, right? It's literally called the step size. Right? That will take me to A prime, which is a better place, closer to the where the loss will be a bit less, isn't it? Does that make sense, guys? And I can keep making hoppity hops here. And finally, I'll come to the point at which the slope would be 0. Why? Look at this. At the bottom of the valley is flat, right? On the other hand, if I end up with B, at B, if I take one step forward, do you gain altitude or lose altitude? Gain altitude. So it means that the slope is positive slope. Because it's positive slope, and do you want to go in that direction or you want to backtrack? You want to make this step. So would you agree that B prime would be the value of B minus some alpha step dl d beta, isn't it? So now you realize that if your guess is either too little or too much, the formula remains the same, isn't it? So you say that a better value of B, let me call it beta prime, is always the previous value of beta minus alpha dl d beta parameter in single variable calculus. It's called the slope, isn't it? This is called gradient descent, because what is happening? You're descending the slope. If you were an ant, you're moving like this, isn't it? So you're doing gradient. And also you can convince yourself this is the fastest way to go to the origin, right? Now let's go in three-dimensional space. See, suppose you have this. Gradient points in the direction of maximum change of altitude, right? Gradient. That's the definition of a gradient. So if I am here, which way should I go? If I'm sitting at the tip of this rim, should I just go around like this or should I go like this? Go like this, right? Steepest. It is steepest in this direction. So you can take the path of steepest descent. Now, generally when you're hiking, it is not advisable to take the path of steepest descent. Right? You do the opposite. You try to take a gradual descent into it. But in calculus, in machine learning, you are a bit impatient. You do want your machine to take the path of steepest descent. So when gradient descent is said, what you really mean, gradient descent along the steepest direction, right? That's what you mean. Go ahead.
So his assumption is alpha is the same, right? Is it okay?
Alpha, it's called the learning rate. So in the simplest case that I have explained, alpha, you have made it a constant. It's called the learning rate. But what happens is, as you learn, for example, when you do the neural networks class, the foundations of AI, you will realize that every part of this equation gets more sophisticated. Alpha becomes a function. It's called the learning rate schedule, right? And this part. So first, let me take you through some of the evolutions. This in high dimension becomes the gradient of the loss with respect to beta. It's just a big brother. It's just a multidimensional, multivariate version of the gradient slope. It's called the gradient, right? And not only this, you must have heard of things like momentum-based gradient descent, momentum methods, etc. So what they do is they replace this with a function of this, some function of this, right? And its previous values. So life gets complicated, but let's stick with the intuition today. Go ahead.
Question, I might be jumping ahead. How do we make sure this is not a local, this is like a local. versus global?
Yeah, very good. In the case of linear regression that we did, remember this equation was, and that's a very good question, it was y minus beta naught minus beta 1 x square, isn't it? With the I things and the summations. Look at this. This is parabolic, quadratic parabolic. It is what people call a convex function, right? What does it have? It has only one. Convex shapes have global minima. So there's a mathematical word, convex function. So convex function, you say a function is convex when it has one minima, but a function is not convex when, if you take 2 points, if you can find 2 points such that a line joining them goes to the curve, goes to the function, intersects the function. You can convince yourself that there is no such point that you can find in a convex shape, but you can find such points in a non-convex shape. That's the definition of convexity, right? So linear regression admits a global minima, and neural networks are the opposite of it. They're infested with countless minimas, huge number of minimas, right? Which is why people used to be very, very suspicious of neural networks for many years, right? They used to say that neural networks won't work because their loss function is not convex, right? But then it turned out neural networks worked. So when they worked, the neural network community had the opposite joke. They said that the rest of the people are suffering from convexivitis. Right? So, well, there's a lot of beautiful theory around this. We won't get into it. So gradient descent is the path, is the way to come to the minima, right? Find the minima or find the optimal solution. Now let's do some real examples and code. Enough theory. Let's get practical. Then you build a regression model. Let's build a regression model. It's literally as simple as that. Those of you who are familiar with object-oriented programming would love the syntax. Model, we're using a linear regression. By the way, why am I using linear regression? Is that the only regression model there? No, not at all. Linear regression is the simplest because we are just getting introduced to the subject. Everywhere I've used linear because it is easy to get intuition. But if you want to change it to something else, let's say random forest or something, and as I said, the world is very fascinating. There are many, many algorithms there. Good thing is if you're using scikit-learn, you just have to change this one phrase. From linear regression, you can make it random forest regression, for example, right? Or gradient XGBoost regression or something like that. Whatever you want to make it, decision tree, all of that.
Quick
So
question.
scikit-learn,
A
yes.
quick question. Why might one choose linear regression over, let's say, random forest or some other?
Because linear regression is interpretable. You see the relationship between input and output, right? You know, like you can visualize it, you can see the relationship. When random forest and these things will make slightly better models, especially if the data is non-linear, you can't use random. You can't use linear regression. The trouble with random forest and these things are, they are black box models. They will only make good predictions, but they will not tell you why they made that prediction.
I see.
It's not so obvious, right? So interpretability is lost. Right. And because we want to stay highly interpretable, this is important. All right, build a regression model. So you build a regression model. Now you say that you see your y hat. Your regression model is a line, isn't it? Linear means you make a line hypothesis. The only question is what it is. Now, whatever hypothesis you make, you will have some errors, isn't it? Some little bit of errors left behind. So you fit the model to the data. Now, you will notice that, see, the model has made it so easy. You might always say, what was the whole point of knowing all the theory? The point is you understand what you're doing and you know when you're wrong. Otherwise, if you blindly use models, you don't even know when the model is wrong. Right? So
when will we know like when to use linear regression versus random forest or other things? Should we like look at the data and see that how it is going,
yes,
or like?
So you look at the data, you build multiple models, but more importantly, it is the errors. And we are coming to that. You sort of anticipated where I'm taking it. There is something called residual analysis that gives you a very good clue whether your model is the right model or is a reasonably good model. And I'm coming to it in a moment. So let's say that you chose linear regression and then you made a prediction. You see that in one line, 2 lines, it is able to fit to the data, and then you give it some value. It will have a slope and an intercept. It is saying that the intercept is close to 0, minus 0.11. Let's see if it looks correct. Look at this data. If you were to imagine a line going through, would it be slightly negative at the intercept? It will hit the y-axis at a slightly negative value. Looks reasonable. What does the slope look like? Let's say if we are at 2, this number has already climbed to about little less than 20, right? At 1, it has climbed to maybe around 10 or something. Let's see. So our slope is somewhere around a little less than 10. Oh yeah, look at this. Slope is 8.3. So it makes sense.
Another question. Sorry. You have that y hat equal to beta 0 plus beta 1x, right? We're
Yes.
assuming that we have only 2 parameters, beta 0 and beta 1. And so there is intercept and model
Yeah.
and slope. What if we have more than one? How do you get the answer? How do you print the answer?
No,
If there
for
are like 10 parameters.
for X. No. So hang on. For this is univariable data, no? Univariate input. So we are fitting a line. A line has only two parameters, but in higher dimensions, suppose you took wind speed also or rain also, then you would have a plane. So it will be beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. And so you would have multiple parameters and you're looking at a plane. A plane, what does it have? It also has a slope vector, right? Like, see, a plane has this. Let me take this example. Are you guys seeing this plane?
Yes.
Right. So every plane will have a perpendicular, a normal. Right? And you agree that that normal uniquely defines the plane, except for the location of the plane.
Yes.
Right? So for example, if I tilt it, the normal also changes. And in a way, what happens is that the beta naught is how far the plane is from the origin. What is the closest distance between the plane and the origin is controlled by beta naught. And beta 1, beta 2, let's say, they are components of the perpendicular vector, the normal vector. This vector will have components now.
Got it.
That is what it is. And that is
and
it.
And you reference it as model.coef _1 _2 and so on?
Yeah. I mean, you literally call it the beta vector, which has beta 1, beta 2, beta 3. And those are pretty much your orthogonal, they're the normal components, the perpendicular parts of the perpendicular vector. That's how you think about it.
Got it.
Okay? So the intuition is very beautiful geometric intuition, guys. This used to be a course I would teach in 3 months. And I've compressed it into 5 days for you. So obviously we are taking more of we are sitting in an aeroplane and flying over vast and beautiful territory at this moment. Right? But if you join the foundational course, of course, over 4 months, we will develop the ideas much more slowly. So I invite you to, well, obviously I apologize if it looks like a marketing spiel, but if you do join my Foundations to AI course over 4 months, you will learn this beautiful, beautiful subject that's changing the world. You will learn it carefully and properly. Right? So predictions from the model, you give it an input, it will make predictions. Oh, by the way, how do we know that the model is good? You try it on the test data, and then you look at the mean squared error and coefficient of determination. Coefficient of determination needs a bit of explanation. It's called R squared. See, it is the explaining power of your model. It can go from 1, means perfectly explains your data, to people often think it goes from 0 to 1. 0 means no explaining power, but there is something worse than 0. Your model is so wrong that it anti-explains, right? It makes worse predictions than the null hypothesis. Right? How can that be? Look at this. Here, you would want to make a prediction, a line going up, isn't it? And a null hypothesis would be a flat line. So what would be something that is worse than that? It would be a line going down, right? So that would lead you into a whale of problems, and that would give you negative R squared. It's really a bit of a shock when you build a model and you stare at the test data and it says negative R squared, right? You know you have been grossly wrong. So, all right, guys. Now came the question: how do I know whether my model is an effective model? Remember, you never say right model. Good model, effective model means it's a good approximator. Your F is a reasonable proxy for the ground truth. How do you know that? What you do is you look at the errors. By the way, the error, what I wrote as epsilon, people also write in the literature, especially statistical literature, with a R. It is called the residual. The word is residual error. The full form of the word error is residual error. The gap between reality and prediction, right? RI. You can plot the RI. Now, when you plot the RI, here is how to interpret this graph. And this whole topic is called residual analysis. Actually, one of the problems I have with a lot of textbooks these days is people feel, this is a very interesting world. in which everybody is in a hurry to write a blog post. The moment they understand a topic, there is a blog post or something or the other, right? Or an article or even a textbook. And when they talk about regression, people often miss doing residual analysis. They shouldn't. Why? I'll tell you how to interpret this. See, look at one segment from 0 to 20. Look at the distribution of the errors. Just focus on one colored line, let's say orange lines, orange dots. Do the orange dots seem randomly spaced out like a bell curve? Like, they're closer to the origin, more closer to the origin, and fewer far away from the origin, far away from 0?
So if you're looking at distribution or predicted value?
No. Don't look here. This is the errors, not the predicted value. This is the errors, residuals, y minus y hat. So what do you expect in a good model, right? If the line is very close to the data, most of the errors should be small, and a few errors will be a little far off. So look at this point. This is a big error, right? Compared to this 0 line, it's a big error. This is a big error, so far from it. But most of them are close. But now, do you notice that as the predicted value doesn't matter. See, the reason is, as you change the input values or the output values, the thing is input value in multidimensional can be x1, x2, x3, etc. But output is only one dimension. So it's easier to take the output value, predicted value, and look at how the errors change for different predicted values. Right? So I look at this range and I notice this pattern. When you look at this box, do you see, has the pattern significantly changed, or it is more or less like that? You don't see. So for example, do you see a cigar here? Or do you see a sine wave here? Or any shape or form here? You don't. When you see this is the definition. There's a term for this. When you don't see a pattern emerge as you go from left to right in the errors, in the residuals, you say that you have homoskedasticity. Right? That is the word, homoskedasticity. Right? And as you will see, it is not always achievable, but when you achieve that, you realize that your linear model was good enough. See guys, this is one of the common fallacies. People think that if my R squared is small, tiny, let's say, suppose your R squared was 0.11, is the model bad? No, it doesn't mean. It might still be a reasonable model. For example, if I were to ask you to predict how many diapers would sell in a particular geography based on certain advertising or sales campaigns that you do, right? And you try to model it, you will often see that your R squared is very low, 0.23, point something. Why? Because the sale is dependent on many factors that you have no control on. There will be macroeconomic factors, isn't it? Inflation may have kicked in, some news may have come in, right? Affecting. The world is not just made up of your sales campaigns, isn't it? Or the particular demographics of that geography and so on and so forth. So there are many variables you haven't taken care of. R squared is telling you the explanatory power of the variables you do have access to, factors that you have access to. And unfortunately, the most common fallacy in regression that people make is they look at that and say, that is the determiner of good or bad model. Right? No, what you do is everything is a factor. If it is low, you get concerned. But you just get concerned. Doesn't mean that you throw away the model. You go back and look at the residual analysis. If your residual analysis shows it shows homoskedasticity, you're doing pretty fine at that particular moment. And do you notice that your errors are also showing a bell curve, like more or less a bell curve? A good sign, right? So both of these show good sign. Finally, you make your prediction, the prediction model, and superimpose it on the data. Is this the line that would be most close to the data? Yes. So you have visually verified that you have a good model. This is as good as it gets, guys. Now, remember Box's famous truism. All models are wrong, but some are useful. So have we built a useful model? We have. We have created a good approximator, good F, as a proxy for whatever the ground truth was. isn't it?
In that residual analysis graph, how might it look like if it did not have good homoscedasticity?
You will learn shortly. Let's go to the next data set.
Okay.
Right. So suppose you go to a data set like this. This data, again, you do the same analysis and description. Oh, look at this data set. It looks like this. Actually, suppose it looks like this. And what can you tell? Can you fit a straight line through it?
No.
Would it be a good idea to do it? So suppose you try, and this answers the question of somebody here, Sarita, your question, how do you know that I should use a linear regression or not? See what happens when you use a linear regression. You get a model, you may get a coefficient of determination, R squared of 53%. You may say, well, maybe, maybe not, who knows? But here is the clue, and this is why I say, when you look at the clue, now tell me, do you see a pattern standing out at you?
Yes.
It doesn't look like noise. You literally see a pattern. When you see a pattern in your residual analysis, that's when you know that you're barking up the wrong tree. That, I don't know. Sarita, are you still there?
But why is that?
Yeah.
But I'm just curious, why is it that a pattern means that the model is not
That's a
good?
little, it gets mathematical. But basically what it means is that, see, there's a bit of mathematics involved. For today, just take it as a fact that it is. But the basic intuition is that you have left signal lying on the table. Your model hasn't captured all the signal, all the relationship. A lot of it is left, residual is what is left behind. Do you literally see signal left behind on this plot? A part of the relationship left behind.
Yes.
That is it. That is why, so residual plot, if it has no signal, it will look like noise. If your model hasn't picked up all the signal, all the relationship, some of the relationship will show up in the residual plot. And therefore, that is the intuition. Sanjay.
So we cannot just go by R squared.
You should not go by R squared. And it's one of the points that people don't emphasize these days, but I do. And then there's a debate about residual analysis and so forth. But to me, it is important.
Typically, if the R square is higher and you have homoscedasticity, that's good.
Oh, that's good. Then, of course, you're in the best of all worlds, right? Which we saw in dataset 1. So see, what we did in dataset 1, right? It was the best of all situations. Your R squared was good. Lovely, 97%, isn't it? Explanatory power, if you look at it, where was it? 94%, 95%. And the data had homoscedasticity here, right? No pattern, nothing. Enjoy this. Life is usually never so easy. Linear models are good approximations in many situations, but most of the time the relationships are non-linear. So let's go back and look at this one now.
But what quantizes the total average error? Which metric?
The last one, literally sum squared error.
Sum squared. Yeah. Okay. Yeah, that also is another factor.
That is right. Yeah. And that will be reflected in the R squared.
Oh.
R squared is literally derived from sum squared error. It is the deviation of sum squared error from the null hypothesis of your model, from the null hypothesis error. Right? So regression. So clearly this didn't work. So you ask yourself, what can I do? What you can do, obviously this is, and if you insist, so suppose you don't do residual analysis, you go ahead and predict, you build your model on top of the data, what do you see? Would you agree that if you had to do a line to fit the data, this would indeed be the best line? Except that you should perhaps not have built a line as a model. That is it. So what you can do, at this point you say, all right, let me, and this is one of the tricks you use, you say, let's do polynomials, right? So here's a statement. Any function can be expanded into polynomials. You remember?
Yes.
Right? So this is your basic Taylor expansion. We can do that. There is a problem with that. How many terms will be in the polynomial though? Is you don't know. If it is, there are two kinds of functions in the world. One are functions that have a few polynomial degrees and you're happy. You just need to figure out what degree of polynomial is enough, right? And then there are functions that are a bit more mischievous, that if you try to write it as polynomial, that will have infinitely many terms. Have you encountered any such function in your lifetime, guys? Think of it. What happens if I throw a pebble in a water, in a lake, and you see the ripples? What is a good function that shows the ripple expanding out? Sine x, cosine, sine, cosine, right? Trigonometric functions. So if you expand out sine x or cosine x as Taylor, I don't know, I'm just giving it to you as a fact because it turns out that you must have done math in your previous lifetime. So sine x has infinitely many terms. It expands to x minus x cubed over 3 factorial plus x5 over 5 factorial, and so on and so forth. There is no end to it. It has infinitely many terms. Here is one intuition, and this is again, unfortunately, I'm doing it so fast. Just count the number of bends. For example, in this data, how many bends in the data do you find? 2. Therefore, you will need a polynomial of at least one more degree. What is more than 2? 3. So a third degree polynomial will be the least you will need to represent this data. Now, when you look at a sine wave, it goes on and on and on. And how many bends does it have? Infinitely many. Therefore, it will need infinitely many terms if you try to do polynomial expansion. Right? By the way, what I just mentioned is the very fundamental result in math. It's called the fundamental theorem of algebra. Well, I suppose it's taught in such an abstract way in schools or colleges that nobody catches the import of this. But this is really the intuition behind it.
Fundamentally constructed.
A fundamental theorem of algebra. That's it. Right? The number of roots of a polynomial, the number of times it will hit the x-axis, will be determined by the degree of the polynomial. Right? So that's how they say it. And then you say, what purpose is it? But so the more intuitive way to say it is the way I said it. Count the number of bends. You'll need at least one more degree. So when you do residual of that, now suppose what I do, I represent the model as a polynomial. I took it as a degree 3. Why did I take it as a degree 3 polynomial, guys? 2 bends, right? Guys, this is a sort of intuition. I don't know, for some reason, you don't find in textbooks written these days on regression, etc. It is very helpful. You can easily, quickly build models, especially when you're in low dimensional spaces. Right? Problem with polynomial regression is there. We'll come to those problems. But at least for simple situations, try polynomial regression and use your intuition. So let me do that. What was the R squared of the previous model? No. In this particular case,
94.7.
53%. And there was very pronounced pattern in the data. I take a third degree and the model looks way off. Now let's take a third degree polynomial. Right? So there will be beta naught plus beta 1 x, xy, x plus beta 2 x square plus beta 3 x cube. Now you know that if it is a sine wave, the beta 2 should be practically 0, because here's the thing, guys, and this is something, again, one of those results of math I'll just mention. Sine wave, is it an odd function or an even function? Around 0, the positive side and the negative side, are they mirror images or they're inverted? At x, what happens? Sine minus x is the negative of sine x or just sine x?
Negative.
Negative of sine x, right? So in other words, it's an odd function. Odd functions, when you expand, they tend to have, in this particular case, for example, odd degree terms, right? And even functions, like when the left and when fx is the same as f minus x, when you expand them, they will only have even degree terms. Why? Otherwise, if it had an x term or an x cube term, you would lose the symmetry. Right? So guys, it's these beautiful little connections of math. In a way, it's there in your mind, but when you reason through it and you bring it to bear in your analysis, it just gives you pleasure. It just helps you do better analysis. Okay, we'll do that. Let's see if our results are validated. We build the model. We look at the coefficients, 0, 2, -1, and 0.12. Right? These are the coefficients that are emerging. Now, let's move forward. R squared has gone up to 96.5%, right? Or 97%. That looks reassuring, isn't it? Mean squared error has declined. And now when you look at the residual plot, do you see any pattern here? Do you see any heteroscedasticity or, yeah, no, it looks nice, pattern-free data, right? And therefore, you feel you have landed upon a good model. And let's plot the model over the data. What does it look like now, guys? Would you trust this model to make predictions for you?
Yes.
That, therefore, introduce you to polynomial regression. That seems pretty good. So, you know, the history of the field is when people had linear regression, we are talking of 1805, then 1812, they were already doing polynomial regression. And right at that time, people are getting pretty, and by the way, that was without computers, by hand, by hand. Can you imagine how hard it was to do it all by hand? So let's go to another data set now. And we say, okay, we'll do the same analysis. Oh, it looks like this.
Quick question. So let's say I had two models and they both had no patterns in the residual analysis.
Yeah,
Should I pick the model with the better R square?
of course. So see, all of these indicators, right? You treat them as supporting evidence, always, right? The mistake that people make, most people make, is they get fixated on one measure. They'll say R squared, that is it, or mean squared error. And don't do that. A thing, if it is, see, there's a statement in science that it takes one experiment to prove your theory wrong, but 1,000 validations does not prove your theory right. Nothing proves your theory to be right, right? But 1,000 experiments give corroborating or supporting evidence for you to have confidence or belief in your theory, belief in your model, isn't it? So when 1,000 experiments validate your model, your hypothesis, you say it's a good theory. It's a good hypothesis. And that's a hypothesis becomes theory when lots and lots of experiments support it, but there is not a single experiment that violates it.
So it is possible then that because I'm using a sample here and not the entire population, and I'm using a sample plot, some sample might give me a pretty good R square and may give like a nice residual plot.
Which brings us to the point of cross-validation. Very good point. So you should never build model with one sample of the data. Go build model with lots and lots of samples of the data and make sure that all those models are more or less alike. Right? Otherwise, you did not pick up a representative sample from the data. Right? So it's like human beings, right? You might have made a mistake. Accidentally, you went into kindergarten and picked up kids and you make a model for height. Next time you have no idea and you stumble upon a basketball field and you build an entirely different model from your data. Well, the data is not quite there, right? As it is literally not sampled properly. It's not representative of the underlying population. So likewise, in a model, what happens is when you take a model on very small sample sizes, it overfits the data. When it overfits the data, the next model you make on the next sample, small sample, will also overfit the data. So basically, you end up with junk. These two models will not agree with each other at all. And that's when you get a clue that you're getting things wrong. So, and again, guys, these are very fascinating, very good questions for you to ask. I apologize that when you do a compacted introduction in 5 days, or just do the whole regression in 1 day. We are talking about a deep and rich field that has evolved over 200 years with a lot into it. So at the expense of sounding repetitive and salesy, want to learn it in a systematic way? Come to our courses, our more formal 4-month courses. We will systematically build up the theory and you'll build foundations for life. So look here, look at the residual. If you do a linear model, bad. If you do, linear model is really bad, right? So now looking at this data, how many bends do you see in the data, guys? 3. So what degree of polynomial would be a good bend? Minimum 4. So here, you can try it out. And now you also realize that this is sort of looks like an even function. So you realize that the odd degrees would be sort of useless. So you should go to at least 9 degrees so that you pick up at least 4 of the even degrees. 0, 2, 4, 6, 8. You picked 4, right? that sort of thing. That's one of the, see, these are little mathematical things that you can have fun with. You can try it with the 4th degree, you'll get some sort of a model, but with the 8th degree, you get even better models. Now, do you notice that some terms are really zero? You can see it. Do you see that? First, there will be a good term, 1.3, and there will be another good term, like then there will be terms that are very small, vanishingly small. Lots of very small terms, right? So when you want to simplify the model, what you can do is just go out and zero those terms. Now look at the residual plot, guys. What do you say? Do you see any very obvious pattern? Little bit is there maybe, but not much. So model is reasonably good. Now, but you can't say that it is completely pattern free. And the reason for that is I generated the data from a sine wave, right? And a sine wave cannot be represented by a polynomial of any degree. So you will have a little bit of a clue that you are probably barking up the wrong tree. So sometimes the question therefore comes, you're barking up the wrong tree, but you're looking at this data, residuals look pretty good. I would use the word pretty good, not perfect. The coefficient of the R squared looks very good. Mean squared error looks very good. At that point, what you may conclude is, hey, it is a good enough model for me to work with, go to production with. So that's a practical decision, because the more time you spend building better models, remember, to get better and better models, you have to spend more and more time, right? So at some point you say, you reach a point of diminishing returns. So unless you're a really clever guy, do that. So that used to be the traditional way of going about it. Then came models like random forest, ensemble methods, support vector machines, and then after which, by the way, support vectors is named, and neural networks. Those are black box models. They actually do an amazing job of building regression models that are very good at prediction. But what you lose is interpretability, right? They become black box models. You have no clue what it is. So suppose a doctor, you're making a prediction. Imagine that you went to a doctor and the doctor looked at all your blood test results and says, I don't think you're going to live very long. So the first question would be, what do I do? I said, I don't know, but you're not going to live very long. Would you like to meet such a doctor again? No. But you would like to meet the doctor that says, hey, you need to exercise more. Just go do that. It's important for your longevity. You would want to go to that doctor. So in other words, you need interpretability in the model, isn't it? So that is the new world. Anyway, we'll come to. So here's the model. We have interpreted it. Yeah, put it like this. So I'm just quickly taking you through different data sets. Let me see what this one was. Okay, this is a parabolic data set. This is too easy. Let me go to 5th. Now let me surprise you with something. Look at this data. By the way, this data is unusual. You never have data without errors. I deliberately generated a data that has almost no errors. You see, there is no spread in the data. Now the question is, what is the function? You may say, well, polynomials are doing very well. Let me try to interpret it with polynomials. And you can keep doing polynomials. Linear regression would be a disaster. You realize that this is as good as you can come to a straight line. Not good. You can go and do polynomial regression of degree 6. The problem is in this, what is the problem? This shape, if you look at this shape carefully, how many bends do you see? Well, it's hard to tell. There's one very obvious hump here, but actually, if you look carefully, the whole thing is bending all along, right? It's hard to tell whether to call it a bend or not, right? So you can do polynomial, and when you do the residual analysis of polynomial, oh, good grief, not what you want to see, right? Nevertheless, if you look at your residuals, you did a 6-degree polynomial, you got a very high coefficient of determination, R squared, and very mean squared error is negligible. What does that mean? This is the opposite situation. You see a pattern in the data, but if you look very carefully at the y-axis, look at that. Those are minuscule numbers, 0.05. Do you see how small those numbers are? Right? And so basically, even though it seems to be a pattern, it's because you're zoomed in. You're heavily zoomed in. Yeah, that is something you have to worry about. And then when you plot your model over the data, would you agree that this will be a pretty good model, pretty respectable for making predictions, isn't it? Right? Now, this is something to look at. And finally, I'll do something else. I know I'll go quickly through this data, guys. I'm doing the same analysis over again, just to show you a variety of data sets. Oh my goodness, here is a snake, right? Here's a snake up there. Does it look like a snake or a rope? Like that. Okay, it has also, how many bends are there? How many of you would like to count? 1, 2, 3, 4,
13.
6, 7, 13. Yeah, exactly. If you look carefully, depending upon how carefully you look, you can count the number of bends. So you realize that linear regression would not yield too good a result. You did linear regression. Actually, if you think about it, there is some part of it has a linear relationship at least, right? So if you build a linear model, you won't be too far off. It will be a rough approximation. You got about 80% R squared. When you do residual analysis, you know you'll see a pattern, isn't it? Right? It gives you a clue that you're not looking, you shouldn't be using linear, you should use something a bit more sophisticated.
In the above example, with the 13 bends,
Yeah.
what if we modeled it as 2 lines, one going down and like a V shape?
You can try that, actually.
Yeah, that one. Yes, this one.
Yeah.
Let's say you had it like a V shape, one line going down and then going up.
No. What is the function that you would use? What you would have to do is build 2 models for 2 different regions. Let's say from 0 to 4, you can make maybe a straight line, flat line. From 4 to 10, you can make a straight line going up.
Yeah, something like that. Oh, okay.
So you'll have to, what is called piecewise model. 2 different models for 2 different regions of the data.
Nice.
And you do see pattern in the residual, giving you a clue. You need to try a bit harder. You go and visualize the model predictions. Obviously, a straight line is not bad, which is why it gave you an R square of 80%.
Hmm.
So,
Question, is there a playground for regression on like just the TensorFlow playground you had? Just curious.
for one dimension.
No,
Actually, in our 3-month course, yes, there is. We have one, right? I didn't because it would be too much effort for me to drag it in here.
That's okay. Just curious.
So, but we have our own playground like Tensor playground for regression. You can literally put dots and make your own relationship dots of data, or give it any data, and you can try different models, and it will immediately show you how these things are developing and evolving. But one day is too little to bring everything into the classroom. So residual plots, what do you see? Oh goodness, there is a pattern in the data, not quite good, right? You took a polynomial of degree 6, didn't quite work, but still not bad, right? Would you say?
Yeah.
Reasonably good at making predictions. You can go to higher degree, 13, 12, right? Somebody saw 5 bends, somebody saw 6 bends, somebody saw 11, somebody saw 13. You can pick your number. And as you pick your number, your residual still is going like this. The problem is the higher degree that you go to, and this is an important point why I'm holding you back. Do you notice that it is going up? But what's happening at the tail? What happens, the problem that happens with using polynomials is, guys, what happens when you use polynomials of high degrees? You may say, why not use a polynomial of very high degree? Your function becomes too flexible. And the problem with it is, it develops what I colloquially, or in my intuitive way, call wagging tails, like your dog. Right? It develops these tails, right? Or a more formal way of saying it is that in the periphery, in the outskirts, it develops oscillations. It will also develop strong oscillations in regions where the data is not rich, sparse, right? By definition, in the periphery, data is sparse because there's an entire region of emptiness, right? This phenomenon was already discovered in the 1800s. It was discovered by the great mathematician Runge, and it is called the Runge phenomenon. And when you plot out, you will see that if you really plot out the model for a longer range, do you see that it shoots up, right? It just becomes weird after some time. So you shouldn't go too high a degree of polynomial. And this Runge phenomenon, I will just talk a little bit about, and the rest of it I'll start summarizing in a bit. See, you can take even a bell curve. A bell curve is another, by the way, those functions, those mischievous functions that cannot be represented with finite terms of a polynomial, they have a name. They're called transcendental functions. And now you say, well, sine, they're transcendental functions actually everywhere. You throw a pebble in the water, the ripples are sinusoidal, transcendental function. The decay of the amplitude, if I'm right, they're either Bessel's functions or Legendre polynomials, one of these two. So anyway, all around you are transcendental functions. If you look at the shape of the cable, electric cable hanging from the poles, it's another transcendental function. Actually, the world is described predominantly, the physical universe is described predominantly in terms of transcendental functions. So they're everywhere, which also means that polynomial regression looks very good. It works. It's a good approximation, but you need more powerful tools. You need tools that can deal with transcendentals quite well, right? Or and you have to, by the way, transcendentals are amazing. I invite you to learn more about transcendental functions, beta function, gamma function, etc. By the way, the last one that I showed you, I didn't mention, but it was a gamma function, I believe, right? So yes, so if you do a bell curve, it's a transcendental function, Gaussian. It will show a lot of pattern in the residuals. A straight line would be a disaster. If you do polynomial, you notice that the polynomial has a problem. What is the problem? At the tails, at the peripheries, it starts showing oscillations. Right? This is the Runge phenomenon. It was discovered by Runge. I forget the year in which he discovered it. 1901 is 1901 is when it was discovered by the mathematician Runge. Right? So it's a lesson, and I won't go more into it. Regression is not the only way you can deal with it. You could have done, for example, nonlinear regression. So for example, if you look at data like this, a very simple physicist question would be, if I suspect it is a sine wave, why do I not model it as a sine wave? Make a hypothesis it's a sine wave. You can actually. That is usually easily. So if you make it as a sine wave, what are the three things you need to know? The amplitude, the wavelength, and how phase shifted it is from the origin, isn't it? Right. So amplitude, wave number is wavelength, and phi is the phase shift. Right. So then the question is, let's build a regression model in which we just try to find what are the best values that fit the data. And when you do that, you can actually, and when you do that, you realize that you have a pretty good agreement between prediction and reality, and your residual plot looks like this. Would you consider this to be a good residual plot?
Yes.
It would be very good. And what happens is here, nonlinear, you can't do so-called R squared. It's not correct. But what you look is the correlation between prediction and reality. So your correlation is 98.5. Very high correlation, right? So you know that your correlation is high, your residual plots are good, things are looking good. And when you plot your model on the data, it looks very good. Okay. Likewise for bell curve, if you know that it's a bell curve, what you need to know is where is the origin, where is the center of the bell curve, and what is the variance, isn't it? And this scary looking equation is the equation of a bell curve. Right?
Why are not residuals not helpful? You're still looking at
that.
Right?
No, they are very helpful. The residuals are lovely. It is giving you a clue that you have built a really good model. Yeah? And likewise, for a bell curve, you can do the same thing and see what happens when you fit a bell curve. Do you realize that what polynomial regression couldn't do, this did it immediately? What is the and this is one of the things I must say. See, we are playing with toy data, one-dimensional data, but this is still true in however complex the data is. Guys, if you can bring your intuition, if you can create a theory or a hypothesis, right, then you can build AI models that are far more effective and more easily. And that delves into one of the topics that we'll explore in our course, foundational, is called physics-informed neural networks, right, and things like that. We'll do a lot of that. You'll see that neural networks, one of the amazing things it does is it solves really hard problems in fluid dynamics and things like that and so forth. So gamma distribution, I can go on, and I won't go on with that. Let's go to, I will just end with real life. So enough of toy data. What about real life? If you go to real life, in California, everybody seems obsessed with the price of a house. Those who live in apartment want the house prices to go down so they can buy one. And those who live in houses obviously want the house prices to go up because they're sitting upon the equity. So the favorite topic in Californian discussions is, how is the real estate doing? Right? So this is a model of house prices based on location and number of bedrooms and so on and so forth. So there are many factors involved. This is it. Now, guys, if you look at this data, you would all agree that these are the two population centers, Bay Area and Los Angeles, right? You can literally see by looking at the population, just plotting the data, exactly where people live in Bay Area, right? In fact, if I just plotted nothing but the median house value, so the darker values are more expensive. Can you tell what does this, just a simple plot of latitude, longitude as the XY axis and the color being the house price, what is it telling you? Is it cheap or inexpensive to live in the Bay Area, or is it very expensive?
No,
Yeah.
very expensive.
Very expensive, right? So this is it. Visualization, again, speaks to it. Now you notice that I visualize the data without putting a map on it. Nevertheless, you can tell that this seems to be the map of California, isn't it? Reality about California. So this is it. Then how many factors are there? Lots of factors are there. And you can do univariate statistics. You can do histogram of each of the components. You can do box plots, violin plots. This is reality. But everything that I told you, you're just extending it to more variables. That's all. So develop your intuition and muscles in single variable and then touch real data, because you bring powerful intuition to it then. Right? So basic regression model you can build. And this is the power transform I was talking about. Sometimes, the easiest power transform you can do is, if you don't see the histograms to be, and again, I'm moving too fast, but I'll give you an intuition. Whenever you look at data, let's say look at this data, this particular graph, this graph, let me look at this graph, median income. Does it look like a bell curve or households? Does it look like a bell curve? No. It has a skew, right? So one of the things that quite often helps, not always, take the log of it. And when you take the log of it, it's called the log transform. It's one of the transformations you can do, power transforms. Your model will be better, right? It's one of the things people forget to do, the power transform of data. Right? So you notice that now, look at this, median income. I took a log transform. What did it do to the median income? Welcome. Actually, believe it or not, sometimes it is these little simple things that helps you make great models, right? Anyway, now you look at the residual plot, linear plot. What do you see? Well, forget about this funky thing that's happening as a diagonal. That's the nature of the data, but sort of not too bad, but not too good. It's okay. Linear is sort of okayish, right? It shows up in the R squared. What is the R squared? 60 to 70%, right? So in other words, linear might not be the best approach. Right? You need to use more good distance. This part of the code seems to be broken. So there is a thing called regularization. We didn't get time to do. Regularization is, well, it's a big topic. When you do machine learning course in detail, we'll talk about it. But let me take another real example, worth ending on the Old Faithful Geyser, which I trust all of you have visited. The eruption times, how much you have to wait for the next eruption depends upon how long the previous eruption was, right? And so you take this data, it looks like this. You plot it out. You can build a model, easy model, right? Regression model. You can build a regression model. And here is if you build a linear regression model, when you look at it, now you do realize that there are certain places, there literally data comes in 2 clusters. So there will be empty space in between. But other than that, the noise seems to be reasonably well spread out. No too obvious a pattern. So a linear regression model therefore seems, oh my goodness, something has gone wrong here. I'll update it and put it there. A straight line would have been going through this data and doing just fine. Right. All right, guys, so we had a long time. I took an extra hour. I hope it gives you some sense of one of the pillars of machine learning called regression. To summarize, regression is to find a relationship between input and output when the output is a number or a vector. Are we together? Quantity. Tomorrow we'll do classification. We'll talk about cows and ducks. And so I apologize, it took us a longer time because we went through NumPy and took a detour, but it is what it is. Thank you for being here with us for so long. And I'll see you tomorrow. By the way, if you guys want to know where the longer courses are, just go to supportvectors.ai and you will see a schedule of our courses. This is the schedule of courses coming up. Highly recommend that you take one of the foundational courses if you want to go deeper into machine learning. And you can explore the details of the courses by going into them. You'll find all the details here. All right, guys. So with that note, I'll end. Good night.
Thank you.
I'll field questions. If you have questions, I'll take. Anybody has questions, guys?
Just one question. You mentioned a little while ago that it's a good idea to take a log transform. But what if I had not taken the log transform and just run polynomial regression and managed to fit it? How would that be pretty much the same, or?
Yeah, so there's a statement, and again, it's a big question. It's a question that needs an interesting answer. In machine learning, one of the most foundational results is called the no-free-lunch theorem. See, when you build a polynomial model or you build a linear model and you do this transfer, you're building different models. The theorem says, and it's a theorem, which means you cannot fight it. It's forever going to be true. It says that data speaks. You need to build lots and lots of models and find out which is the best. You need to do a lot of experimentation. So this field is about curiosity and experimentation to see what works.
Mm-hmm.
It's a lot of hack work. If you notice, new models keep coming out in AI. A lot of them almost all of them are discovered through experimentation.
Thank you.
Any other questions, guys? I hope you did have fun. So run the code, guys. Play with it. See if you can review it. And we'll meet tomorrow to do classification.
Asif, one thing I noticed was in your examples, if at all, if the Python package was added within the cells, at that time it does look like there are errors when you run it actually. So at that time, do you have to update the?
No,
like you have to do UV sync upgrade by adding it to the package file or something.
See, here's the thing. We do like wherever I see pip install or something, just delete it. See, UV has matured recently. We haven't had time to clean up all of our.
That's fine. No. I saw like most of them run. There is no problem. Only places like certain places where we add like a new package has been added, like import some certain thing as this one, which was not.
No, if you point out specifics, post it to that. It shouldn't be like that.
Sure,
it should not.
Okay.
Like I don't know where you notice. If you tell me specifically which notebook, I can look at it.
And the first data set 1.
Data set 1.
Yes.
Where do I say import?
Import missing number.
Imports are harmless. See, import missing number, this, blah, blah, right? No, this you need. You can't avoid this.
No. When you run it, it gives an error telling that the missing number package is missing.
Oh, then what you do is you go to your project and you just do UV add missing no.
Oh, okay.
I apologize. Let me see. Did I forget to put that there? Py project missing number. Oh yes, indeed. That is here it is. So I don't know why it happened. Just do UV sync upgrade and things will be fixed.
Sure. Okay.
Make sure you do UV sync. You should keep doing UV sync upgrade all the time.
Understood. Okay.
So thank you for the session.
Yes, I'll see you tomorrow.
Thank you.
Guys, let me finish with the remote ones and then you guys stay here. We'll talk. Yeah, go ahead. Anybody else has a question? Remote on the remote Zoom.
Yeah, Asif, just a question. See, there were some errors in few of your examples, right? So once you correct that, we just do a UV sync upgrade and it should update.
That is right. That is right. We post it actually. We put this together. See, we are transitioning all of our notebooks to the UV packaging. We will see also in Python, this is a nuisance. See, what happens is these open source libraries, their versions keep getting updated and they keep breaking each other. So what happens is all the time you have to keep revalidating that everything works.
Sure.
For code, it is easy. See, when you have scripts, it's easy. But because you have unit tests and you have all of these. But for Jupyter notebooks, it's hard because you have to literally go into each notebook and run it one by one. Right?
Got it.
So is the source code available in the same notebook? Or?
It is there, literally.
Okay.
Source code is right here. This is the source code.
Oh.
This is in machine learning, right? Source code is literally this size, no more than that.
What the data? How do I import the data?
Oh, that also is here. If you're looking at the data, right? Let me show you.
Yeah.
When you go to, let's say, docs, notebooks, you will see there's a data set. There's a data set. Okay, somewhere. If you go to most of, you notice that ls_star.txt is here, ls_star.csv is not here, and cd.
Okay,
Yeah,
so the code will pick the data from here and then. Okay.
Yeah, so we point to, and what happens is sometimes the data, if it is reading the data, it will tell you where it is reading the data from. Let's look at this. It's reading the data literally from this URL.
Oh, okay. From
so what we have done is we have taken a lot of the data and made it public.
Okay, okay. Yeah, fine.
So it just picks up the public data directly.
Okay.
Guys, I'm going to close. I'm going to get out of the Zoom. If there are final questions, if anybody has, otherwise I'll stop. I'll see you guys tomorrow then. Bye, guys.